Hello everyone, I'm going to talk about corner detection using the Harris corner detector and about the detection of lines and circles using Hough transform. First of all, I'm using Julia this week because it just combines the best words of interpreted languages like Python and low-level languages like C. We have speed that is almost as fast as C itself. But we have a very nice development experience because we can use Jupyter notebooks like in Python. For example, it is very easy to just load in some image here and it gets displayed in the notebook. Okay, anyway, let's start with the Hough transform. First of all, I'm going to show you some image here, which is just an image with two lines in it. This is actually the original image, but what we need to do to compute the Hough transform is we compute the edge image first. That's why I call here the Sobel function. The Hough transform wants to find lines in an image, so any lines that run just straight through the image, and in this image here we have two lines where we have a chance to detect them. Let's see how it works. First of all, let's take a look at the function Hough transform accumulator matrix here, and this function here takes as an input an edge image where we suppose that in the edge image all the dark pixels that are close to black have a value of 0 and the white images and the white pixels have a value of 1. And what we have here as well are two other parameters. First of all, a resolution that defines the resolution of our parameter space, how fine-tuned we can find different lines in the image. And the second one is a threshold, which basically says how bright does a pixel need to be to even be considered to lie on a line that we want to find. Because pixels that are darker than the threshold, we will just say they are not on a line, because we think that lines should be bright, because we have done the Sobel filter before, which should bring out all the edges as very bright in the image. Okay, so let's see how it works. First of all, we try to find edges in the image. No, we try to find lines in the image, and each line can be defined by two parameters. And usually, as you know from school probably, let's say we have this line here, which goes through the image. We can define it by the parameter n, which would be where it crosses the y-axis, and the parameter m, which is like the slope of it. But there's also different parameterizations which we want to use in the Hough transform, and that is by using something called phi and r. So let's take a look at this line here again, and let's take the different parameters phi and r. Phi is basically an angle, so if we start here we can draw an arc, and we can just say here's 0 degrees and here's 180 degrees, and each line that we have in an image here, basically if we draw a line perpendicular to this line here through the origin, which is in the middle of the image, then we get the angle here. So for example, this line here would be parameterized by an angle of maybe, I don't know, 160 degrees or something. And the second thing is the radius. And because the angle can just be between 0 and 180 degrees, or between 0 and pi if we calculate in radians, the radius needs to be able to be negative as well. So for example, for this line here, we would expect to have a very high angle here, like this, and then a radius which is negative to this side, which goes like here. Maybe if this is 100 pixels here, half of the image, then maybe the radius here would be 50 pixels or something. So these are the two parameters, and we want to find which parameters are most likely to characterize lines in the image. And maybe you wonder, why is the arc here to the bottom and not to the top, like we know it from maybe math lesson at school, where the arc is usually drawn like this? It's just because in the computer, when we have an image, it is a two-dimensional array, and it goes usually from top to bottom. So for example, this is the x direction here, and this is the y direction, and that's just why the arc here is turned head over. We'll see it in an example in a moment. So first of all, we need to fill a matrix where we divide our parameter space. So for the phi from 0 to pi, and for the radius from maybe minus half of the image to plus half of the image, we need to fill this somehow with counters, like we count every time a line matches these parameters. And to do that, first I calculate for every possible value in the parameter space. For phi, I calculate the sine and the cosine. That's just the thing I do for performance optimization, because then I don't need to calculate the sine and cosine, which could be very costly every time. And then actually the fun begins. First we initialize a matrix, which we call our accumulator matrix, which has the shape of our resolution, and the resolution is how many dividings do we want to have on the phi space and how many dividings on the r space. And then we basically iterate over each pixel in our image, and for each pixel we just check, is this pixel greater than the threshold, and if so, then we iterate over all possible phi values and calculate what would be the relating r value that we would need. So for example, let's go back to the drawing board here. Let's say we have a pixel. I'm going to choose yellow color. Let's say we have this pixel here. Okay, yellow is really hard to see. Let's pick a different color. Let's pick red again. Okay, let's say we have a pixel that lies here. So first of all, we take maybe an angle of just this here. We have an angle like this. What would the radius be to have a line that goes through this? So for this, the line would need to go perpendicular to this. So this here, this is then the radius. And then we do that for the next discrete segment of this arc here. So for this maybe the line would need to go this, so the radius is a bit smaller. And then for this we go like this, and we basically calculate the radius for every possible phi that we have. And that's how we fill the accumulator matrix with a bunch of values which are all greater than 0, and they are all integers. And in the end what we need to do is we normalize the accumulator matrix to have, we basically divide each element just by the maximum, which we calculate here on the fly, the maximum each time we fill the matrix. And then the accumulator matrix is just a 2D matrix with just values between 0 and 1 in it. Let's see how that actually looks like. So let's calculate the matrix, and it looks like this. And we can see in this matrix here that we have two very bright spots. And let's see what these spots actually relate to. As you can see, let's take this spot here first. So what you need to know is that this direction here is for the phi, and that this direction here is for the radius. So actually, this spot here, what we have, it is a phi which is exactly in the middle, I would say. Yeah, pretty much in the middle. So what is that in terms of the image that we have here? Let's pull up the image again. Let's put it here. So let's imagine the coordinate system here again. A phi that is exactly in the middle is basically 90 degrees. So it goes down from the middle just here. So this is the phi that we have. This is our phi here for this point here. And then the radius here, we can see it's a bit more than half of the image here, so it's a bit positive but not very positive, and that basically relates to a small value like this here. So we can see we got a bright spot here because of this line here. So we can see with our own eyes that this spot here just relates to this entire line here. Because of all the bright pixels here, we get accumulated values high in this space. And probably this spot here relates to the other line. But let's see what happens next. So we can basically specify now a number of line segments, how many we want to have. For example, the top 3, or here I just take the top 10 line segments. And a line segment always relates to one pixel in this accumulator matrix. For example, this one pixel here or this one pixel. So we take the top 10 brightest pixels here using this function that I wrote. The function is not really interesting. We just go over the matrix, take the top, we sort all the pixels, and then we just take the maximum 10 pixels. And if we then look at these, I wrote some function to plot the linear functions through the image. So these are the top lines that we could have, the top 10 spots in our parameter space. And we can see that there's a big problem. First of all, we just have 2 lines. So what we want to try is we just want to take 2 lines and not 10 lines. But now we see if we take 2 lines, we actually don't get this line and this line, but we get 2 lines that are very close to each other that both characterize the bottommost line. So we need to do one other trick to come close to the solution, and that is non-maximum suppression. As you can see, in this accumulator matrix here, near to this very bright spot, there are other very bright spots. And that means we have multiple lines that are maybe among the brightest, but they are almost the same, and we don't want to have that. So we need to do something called non-maximum suppression, where for every pixel in this accumulator matrix, we just compare it to all the 8 pixels around it, so in a 3 by 3 square. And every time it is not the maximum of these pixels, we just set it to 0. So we completely suppress it. So hopefully only the maximums remain then. So if we apply this, let's see what happens. Then we get a matrix that looks like this. We can see around this white spot here, everything got suppressed, and then probably this spot and this spot are just the ones remaining. And if we run this again to get the top k line params from this suppressed accumulator matrix here, and we just take the top 2, then we can see that it actually relates to the lines that go directly through the image. So let's take some more complicated example. For example, this here with a bit more shapes in it. Now we can get the accumulator matrix again. We can see we get much more complex pattern in here. Then we need to suppress it again. So now we just get a few bright spots. And let's try to see maybe the top 5 bright spots. And we can see that it actually relates pretty close to all the lines that we have in the image, to the 5 lines. 1, 2, 3, 4, 5. Yeah, so another thing that we can do is we can define a function which plots all the intersection points between the lines. And that can be actually used to find the corner points, because a corner is basically where 2 lines intersect. So that would be really good to display that. Let's see it, how it looks like. And then we can use the Hough transform basically to find corner points. Here's a corner, there's a corner, there's a corner that is pretty close. But it also detects a corner maybe around here, which first of all doesn't make any sense. But if we take a look at the lines again, yeah, there are 2 lines intersecting. And it gets even worse if we take a bigger image. For example, this is an image of a house. I'm going to show you the original image as well. So this is the original image. We calculate the Sobel image again to get just the edges of the image. And now we would try to find with the Hough transform all the lines that run through. So we calculate the accumulator matrix again, do the non-maximum suppression, and then we can find a lot of line parameters here. Let's display them, and they look like this. We have crazy lines, and it mostly here, for example, these lines here, they first don't seem to make any sense, but the thing is that we have such a huge accumulation of white pixels over here. We can see that it basically runs through there and it makes sense. But the corner points don't make any sense at all, because there are so many intersections of lines over here, even though there are not even bright pixels. It doesn't make sense to take all the intersections as corner points. This is really horrible for finding corners. That's why there is the Harris corner detector to find corners. And I want to present to you now how this works. First of all, let's go to the function here and see what actually happens. So the Harris corner detector takes an image again and then 3 parameters. First of all, an alpha and a threshold. Let's see what the operations here do. We take the image and we first need to smooth it. And then we apply 2 functions. We take a gradient in the x direction, and a gradient in the y direction, and then we have 2 gradient images. And these gradient images, we basically square each to get the images A and B, and then we also multiply them with each other to get something like C. And the goal here is to find points where the gradient in one direction is very strong, but also in the other direction, because a corner is a point where the gradient is strong in multiple directions. If we have an edge, the gradient can be very strong, but only in one direction. But if the gradient goes in multiple directions, there's some kind of corner. And then we just apply this formula here, which I just took from the slides where the formula was specified. And also on this matrix here, we also do a non-maximum suppression. And then we basically get our corners by just iterating over this matrix here, which contains all the corner strengths. And if a corner strength is above the threshold, we just add it to the list of corners. And this gives us a lot of corners. And the last thing we need to do is we need to clean it up. So for each of the corners, we check each of the other corners. Is there a corner that is very close to it? And the important thing here is that we first sort the corners after how good they are, so that the best corners appear first. So from the corners, first we can just pick the best corner, but then we iterate over all the corners again and see if the corner is close to this corner, we cannot add it to the good corners, otherwise we can do it. And then we iterate over it again and again and again. So this takes a lot of computational power, as we will also see in the runtime analysis. But in this way, we can basically eliminate a lot of pixels that are close to each other, similar to how we did it in the Hough transform. It's actually exactly the same function here I use for the non-maximum suppression as I coded for the Hough transform. And by this, we get a lot of the good corners. And yeah, let's see the result. So for this image here, the geom image, I'll show you, it looks like this. We already had it here. We get 9 points by this way. Let's plot the points here, and we can see they pretty much closely relate to corners, way better than what we had before. Let's see it on a bigger image. This is the house image again. It takes around 2 seconds. Let's run it again. Maybe it's faster. No, around 2 seconds to run it, and we can see the corner points are pretty accurate. It gets a bit irritated by some noise in the image. Maybe we need to do some more smoothing, but overall it pretty much finds all the good corners, and it doesn't show any weird corners like in this area here. Okay, so that was it for corner detection. Now I want to show you another application of the Hough transform, and that is for finding circles. Basically, we can find any shape in the image that we can parameterize by some parameters. And a circle, if we think about it, let's take an image of a circle, maybe this ball here. A circle we can parameterize by 3 parameters. So in contrast to a line, we need 1 parameter more. And that is first, where's the center of the circle? So that is first the x of the center and the y of the center. And then also we need a radius. So 3 parameters like this. Now I'm going to show you for the circles how the Hough transform works. Hough transform accumulator matrix. Wait a moment. For circles, it's like this. We also give it an input image, and as the resolution now, because the parameter space is 3-dimensional, we need to specify how finely grained we want to have it in 3 dimensions. And again, we have a threshold, and then basically for each pixel, we just iterate over all possible circle middle points and just calculate every time how far would this pixel be away from this middle point. So for example, if we iterate over this pixel here right now, then we would first take in this row maybe this as a middle point, we calculate this distance, fill in this radius in the accumulator matrix. Next we take this as a potential middle point, fill in this radius in the accumulator matrix. And this is the way we fill the matrix, which is done in this function here. Let's see how it works. So first of all, we can load the image of the ball. We apply the Sobel filter again to just get the edges, and let's see if we can actually detect the circle here. So if I run it and I take the top 3, then we can display them. I define a function here just to then actually draw the circle. And we can see the top 3 circles that the Hough transform found are pretty close to the real circle. Let's just display the best circle, and we can see, yeah, it's very close to it. It can get better if we make the parameter space even more fine-grained, so maybe 100 times 100 times 100, but it gets also very computationally expensive. Because here already, you need to imagine for every bright pixel we find, we need to do 32 times 32 calculations. So that's, how many is that? 32 times 32. So that's 1024 operations for every single pixel. So in a bigger image, this would be probably way too expensive. So let's take a real life image of a circle. Actually, I want to take this image here. Wait. It looks like this. I found it on the internet. It is a building which looks like a circle. And if we just take the Sobel image of it, it looks like this. It's very noisy, and let's see if we can find a circle. So we run the Hough transform on it. Yeah, it takes quite some time because the image is pretty big, so 5 seconds, and it finds this as a circle, which is obviously really, really bad. And what we can do now is we can just smooth the image a bit more. So I programmed this function here, which just does the simple Gaussian smoothing, but it applies it 100 times in a row, and then we get this smooth edge image. And if we now apply the Hough transform, it actually works a lot better. Let's see how it works. So here, there's the circle, and it comes pretty close to the real circle, which is pretty nice. Yeah. Okay, there's another image I have which has actually some circles in it that I drew, and if I apply the Hough transform again, it finds this here as a circle, this as a circle, and this as a circle, which is wrong. So I think the circles here are a bit tilted and not so nice. And also this circle is so small that maybe it doesn't contain enough pixels to fill the accumulator matrix enough. And I didn't control for this. So that's maybe a problem. Yeah, so let's do some runtime analysis. So this time I take a 4000 times 4000 image, which is pretty big. And let's see how long the Hough transform takes. In the Hough transform, I was really surprised by this. It's actually pretty quick. So the main thing is, because in this image and on most edge images, we have a lot of black space and just a few white pixels. And as you remember, the Hough transform basically skips all the black pixels and just looks at the white pixels. So that's a huge advantage. So this just takes 200 and it just takes 0.79 seconds. Sorry, I forgot how to pronounce this. Yeah, and the thing is, if we do a lower threshold here, it has to go over much more pixels. So let's see how long that takes, and that takes over a second now, because we lowered the threshold. And for the Harris corner detector, we can also let it run on the 4000 times 4000 image. And this really has to do a lot of work. The matrix operations in the beginning, they are not the issue, but in the end, as you can see here, we have 3000 points detected, and these are just the good corners in the end. As you can imagine from the code here, let's look again at the Harris corner detector. We first have a lot of corners here, and then we just print out the good corners. And if we actually let's check how many corners we have here. Let's print the length of corners. It's probably a lot. We need to reload the entire module here again. Come on, load it. I would like to see how many corners we have, because we need to sort all the corners and then go through each of them and compare all the distances with each other. And I think this is why it takes super long to do that. So the matrix operations are not the issue, but finding the corners. Yeah, okay, 11,000 corners we found in the beginning. We need to compare each of them with each other and compute the distance. That takes just a long time. You can see here that we have more than 11 million memory allocations while running over this image. And that's why we cannot use Python for something like this and need something like Julia, which is very fast. Okay, thanks for your attention. That's it.